Well, good morning, everybody, and welcome to the first of today's online web sessions or webinars from Smart Vision Europe. My name's Jonathan Quinn, and today we're going to be talking about how to interpret significance tests. That's the first of three webinars we're running. The next one we're going to be running at 1 o'clock is about correlation analysis. And after that, we're going to be looking about 3 o'clock, I think, at neural networks. But to begin with, we're going to be looking at how to interpret significance tests. This is a web session we've run before and has proved to be quite popular with people. If you haven't joined in these sessions before, there's a few housekeeping points we might want to point out to you. One is that the session is recorded, so you'll be able to listen to it again. And in this particular session, there's a lot of slide work because that's how we're teaching the concepts of significance testing and probability and all of the associated elements with the paradigm of significance testing. So we'll email a link out to you afterwards so you can download a PDF of the materials. And if you think it's particularly relevant for colleagues who are unable to join today, and you can get enough of them together, it may be possible for us to rerun the session on a private basis. The best thing to do is just to send us an email or give us a call or something like that, and we'll see what we can do. Now, with regard to asking questions, all the lines are muted. So we ask you to use the chat panel. I generally don't check the chat panel as we're going through the session because in this particular webinar, there's just so much to pack in, and we're going at a fair pace as we're going through it. But my colleague, Rachel, will be fielding some of the questions as we're going along. She's also online, making sure everyone's logged in correctly. And she'll be monitoring that. But more commonly, we tend to follow up afterwards. So when people ask questions, we tend to make a note of who they are and what their email address is, and then answer those questions offline afterwards. That's something we do on a regular basis. If you don't know who we are Smart Vision Europe, and we're a gold accredited partner to IBM and the company called Predictive Solutions and Data Robot, and we specialize in advanced analytics and big data technologies and statistics. And so we also work with open source technologies like R and Python. And as a team of people, we've got quite a lot of experience of working in statistics and advanced analytics and data science and that type of stuff. More than, in my case, about 30 years of doing so. That means we've got lots of deep experience of applying everything from data science to classical statistics to reporting and everything to do with data analysis across many different sectors and many different applications within those sectors. Okay, with that over, we can talk about what we are going to talk about today, which is our agenda and what we mean by the term significance testing, where that term comes from, and introduce you to the concept of inferential statistics and how significance testing relates to that. Then how to interpret p-values, the correct interpretation of that. And then we look at 3 different examples of where significance tests of one sort or another are applied. One is where we look at combinations of category fields. And we look at the chi-square test. That's one of the sort of 101 tests that are introduced to students of statistics in their very first classes. We're also going to look at correlations, which give us a kind of an important lesson on when something is significant, but not that notable, not that significant in the general sense. And lastly, interpreting confidence intervals correctly, just because it's a commonly misinterpreted statistic and it relates directly to significance testing, i.e. finding, to use the term, significant differences between groups. Okay, so the first thing we encounter is the fact that significance is a really troublesome term. Most statisticians really don't like it, myself included, because it implies a great deal, which is not accurate. So it's kind of an inaccurate term. One of the issues is that it implies it's notable, and as we'll see, that it's possible for things to not be that significant or notable. The person who's kind of responsible for it, to a degree, if responsible is the right word, is Sir Ronald Fisher. He's kind of the granddaddy of certainly classical frequentist British statistics. So R.A. Fisher, as he's known. And he introduced the term tests of significance from a book in the 1920s called Statistical Methods for Research Workers. Unfortunately, saying that something is statistically significant is likely misunderstood. Sometimes you hear politicians talking about it and they say, well, this is a statistically significant study. It doesn't really mean much when they say that. In this context, significance does not mean notable. It doesn't mean it's interesting. It doesn't necessarily mean it's reliable. And even the term test is slightly problematic because when we talk about tests, we tend to think of things like COVID tests and pregnancy tests and things like this, and tests of, they're pretty objective and pretty reliable and pretty accurate. But test here is probably should be replaced with the term estimate, because it's kind of more of an estimate than a test. Significance tests are probably more properly described as probability of evidence estimates, but we don't think anyone's ever going to use that as a description. But if you wanted a literal description of what a significance test, it is the probability of evidence. It's an estimate of the probability of evidence. So it's not a test at all. So the people who came up with a lot of the terminology and the sort of scaffolding around the architecture, if you like, around what most people are taught in universities when it comes to what we call frequentist statistics. It's the kind of classic statistics that comes from the 20th century. These guys here, R.A. Fisher, Karl Pearson, Egon Pearson, who's Karl Pearson's son, and Egon Pearson's co-worker, Jerzy Neyman. So you hear about Pearson and Neyman, it means those two guys are kind of the next generation up. So a relatively small number of people who came up with all of these terms and came up with all of these concepts like chi-square and null hypothesis and significance and F-tests and confidence intervals and alpha levels and probability distributions and Z-tests and all this sort of stuff. If you've ever encountered these concepts, it comes down to about these four guys, and they didn't necessarily agree with each other. So as a result of that, the kind of landscape of statistics that they created is somewhat kind of inconsistent and a bit muddy. That's a fair way to put it. I would say it's not an exact science in the way that physics is. It's more sort of a series of compromises that have been made to try and address certain questions in data, which is normally around the idea of is what we're looking at, is it actually real or not, or is it just random? So this approach to statistical analysis is often referred to as the frequentist tradition. You may not have heard that term before, but that's what that kind of approach is called. That school of thought, if you like, is called the frequentist school of thought. And the reason why that's become more important is because there's an alternative school of thought which has come along recently called Bayesian, of which we will talk about in a little bit more detail later, but not too much detail. So the first thing we need to talk about is inferential statistics and significance tests. Significance tests are associated with what are called inferential statistics. That means statistics that make an inference. And the reason that that's important is because at the heart of statistics is the concept of a sample. A sample is a characteristic. A statistic is a characteristic of a sample. Statistic coming from state. There's a state within a sample, a state at a particular point in time. And samples are, of course, drawn from much larger groups. They're drawn from a group called the population. So if you take a sample of water from an ocean, it's just a sample, but the ocean is the population. And the values associated with the population are called parameters. So statistics are used to estimate parameters, to try and guess what parameter values are, which are kind of the true averages, the true relationships, the true median value, the true total amount or something like that within the ocean of data that exists out there. And that's important because obviously there's a big difference potentially a big difference between the sample that you collect and what's actually happening out there in the population. And that's where inference becomes important. So how do we infer a parameter value of a population from a sample statistic? Well, if you think about some of the issues we're going to have here, is that if we go and collect a sample and we're trying to figure out what are the mean ages for men and women in a population, we can go and collect a sample. We might find that the mean ages are 34 and 32, respectively, for men and women. And if you collect another sample, you might find that the differences are different now. The mean ages are in fact 33 for men and 30 for women. If you go and collect another sample, it may be you get the opposite relationship. You get the difference is reversed, where men are on average 31 and women are on average 32. So that means that samples from the same population often produce different statistics when we produce different samples. So samples vary from one another. So we'll never get to the point whereby we can collect a big enough sample for it to be 100% accurate. There's always going to be some degree of inaccuracy to it. And more importantly, somebody else can go away and collect another sample, and their results may be different. So samples vary from one another. And that's important because statistics is the science of variation. It's what it's trying to do is to account for variation. Pretty much anything you do in statistics is about trying to account for variation. And it's the best way to describe it. You know, it's not about data analysis, stuff like that. It's the science of variation. It's trying to account for variation. Some things vary and it's random, and some things vary and it's not so random. You know, there may be some sort of influence or effect that affects this variation in one direction or the other. Is it possible, for example, that the mean ages are actually the same in the population? We might start to ask these questions as we collect these data. And we say, okay, look, here the mean ages here for men and women. You know, is it actually possible that this difference of 34 and 32, that in reality the mean age is that you know, men are 32 and women are 32, and that's actually the mean ages, and that these differences we're observing are just artifacts of the fact that we're taking samples and not looking at the true, not being able to find the true parameter values within the population. So to understand that, we have a significance test to try to address whether or not the differences we're observing are significant, or the relationships we're observing are significant. So we need to talk about significance tests before we kind of return to this question, first of all. So let's talk about significance. Where does the term significance come from? So significance, as we said already, does not mean noteworthy. Instead, these tests simply indicate potentially that the evidence doesn't support the assumption there's no difference between certain groups in the population. Now, that's hard to understand there because it's a kind of a double negative. The evidence does not support the assumption that there's no difference between the certain groups in the population. The idea is that you start from the standpoint and say, okay, well, maybe they're actually the same. There's no difference. Maybe they're actually the same. So it's kind of like saying the evidence does not support the assumption that they're the same, that there's no difference, that they're the same between certain groups in the population. How's that evidence presented to us? Well, it's presented to us in the form of a probability value. And one of the things that's really difficult for people to understand or to appreciate, understandably, which is perfectly reasonable, is that these probability values, particularly in tools like SPSS, are presented with different labels associated with them. So they're not even consistent from one test to the next. Sometimes they say SIG, sometimes they say P, and sometimes they say prob, and sometimes they have much longer labels like asymptotic significance, but they are interpreted in the same way irrespective of the label. So here SIG is shown as 0.001. If we convert that into percentage terms, and this is something that statisticians get used to, that actually means 0.1%. It means, you know, 1,000th, if you like. So it's 1%, 0.1%. A value of 0.172 actually means 17.2%. So you're always multiplying by 100 in your head. You'll sometimes see 0.000. That does not mean that the probability is 0, that there's a 0% chance that something is true or not. It just means that it doesn't have enough decimal places to display it. It's never 0. There's always a number there. So sometimes you'll get too small to display, and sometimes you'll get a label like this, asymptotic significance, and it might have a probability value of 0.034. That just means 3% or 3.4% if you're rounding. So the point is that it's going to have these numbers. These numbers you can turn into percentages in your head if it makes it easier. You're not used to interpreting probabilities. So 0.17 is 17.2%. 0.01 is 1%, 0.03 is 3%, 0.5 is 50%. And the second thing is that they'll have these different labels associated with them. Ignore the labels. Just imagine they all say PPP or prob or something like that, irrespective of the label. The label is just some inconsistencies in how these algorithms and these tests have been presented back to users. And after a while, you start using these tools, you don't really notice too much about whether it says SIG or P or prob or something like that. You get used to interpreting them in the same way. So if we assume there's no difference or no relationship between the two groups, and we were to ask for one of these P or SIG values or significance values, we could calculate what's called a t-test. And a t-test is appropriate for this particular situation, because what a t-test does is it compares pairs of averages, and these happen to be pairs of averages here. So two groups here, men and women, with averages. And if the p-value here is equal to, for example, 34 or 32, we don't know what the sample size is and what the standard deviation and stuff like that and how varied it is. But let's say that, it's 500 people or something like that. And it gives us a p-value of 0.111. It basically says that you'd see a difference as big as this 11% of the time. That's what it's saying. If we see a difference here of 3 years, 33 to 30, we might get a value of 0.04. And it's saying we'd see a difference as big as this 4% of the time. And if you got quite a small difference here of just 1 year, we would see a difference as big as this or as small as this, if you like, depending on how you want to interpret, 33% of the time. So this is how we're interpreting these p-values. We see a difference as big as this or as small as this, X percentage of the time. So we're walking up to the concept of what we conclude from these p-values. At what point do we say, oh, this is, to use the dreadful term, significant? Well, the thing is that significance testing is associated with what's called hypothesis testing. And that means that whenever you're doing a significance test, you're actually testing, you're supposed to be testing a hypothesis, and there's usually an implied hypothesis associated with the significance test. So in this case, the implied hypothesis is that maybe the mean ages for men and women in this population are in fact the same, and we're trying to figure out how likely that is. So if you're investigating relationships with statistics, it's usually because you're curious to see if there's a difference or pattern. That makes sense. You've gone to the trouble of collecting that data. You're usually looking to see if there's a difference or a pattern. So that means you have some sort of hypothesis, at least implied. Example, I think there's a difference between the average age of men and women in my population. If that's what you think, actually, I think there is a difference here between the average age of men and women in the population. That's actually called an alternative hypothesis. It's the hypothesis where you think there is a difference, where you think there is something going on. And you think there is a relationship, and sometimes it's labeled H1. But in reality, your p-value is interested in the null hypothesis. It's really pointed at the null hypothesis, saying you're testing to see if your data supports the idea that there is no difference between the average ages of men and women in the population of interest. And this is called the null hypothesis, and that's called labeled H0 for short. Now, the relevant test then calculates a probability, and this p-value indicates is based on two concepts. One is, if the null hypothesis is true, if there's no difference between men and women and the average ages of men and women in the population, how often would we get a result as extreme as the one we observe? And what do we mean by extreme? Well, extreme is a difference of 1 here, a difference of 3 here, and a difference of 2 here. So that's kind of, there's a way to encapsulate that difference in a statistic, and then to look that difference up and say how often that occurs in a t-test. That difference is called the standard error of the difference. It actually takes into consideration not just the difference, because of course it has to take into consideration the sample size. There's another element in there. It has to take into consideration the spread within the data, how much it varies. So that's the standard deviation. So it's actually it's looking at the difference, it's looking at the sample size, it's looking at the standard deviation, it's encapsulating them all into a single value, and it's saying that value, the larger it is, you know, the bigger the difference it is that you're observing, and that allows us to say how often would we get a result as extreme as one we observe. So those two elements are really really important. So the null hypothesis, if the null hypothesis is true, if you think about it in this way, I sometimes think students have a problem getting their head around that. Think of it as if we lived in a universe where the null hypothesis is true. So how often would you get a result as extreme as the one we observe? If you live in a universe where all coins are equal, and you flip a coin and it comes up 99 times heads and 1 time tails, you're saying, well, I live in a universe where all coins are equal. How often would I get a result as extreme as the one we've observed? It's never saying that's impossible. That's the point. It's never saying it's possible. It's just saying that's weird. How often would you see a result as extreme as that? So that means we have to make an assessment of whether or not the null hypothesis is likely. And whether or not it's acceptable. So that's usually takes us into the realm of accepting or rejecting the null hypothesis. So we're thinking about this difference and its associated probability. Well, how large does this probability value have to be before we decide that the data doesn't provide enough evidence to support the null hypothesis? I mean, should it be 0.32? That'd be 32%. 32% seem a reasonable threshold. Maybe it has to be 0.0001. It's a tiny percent. It's like what, 0.01%. It's like 1 in 10,000. Does that seem reasonable? I mean, clearly you have to choose some point in that p-value to say, I think there's enough evidence to support this null hypothesis, or I don't think there's enough evidence to support this null hypothesis. And the key here is that point is going to be arbitrary, isn't it? I mean, there's no magic number. You're just going to choose a line and draw a line in the sand. So that threshold, that point, is known as an alpha level, and it is fairly arbitrary. And depending on the context in which you're working in, it can be a smaller value or a larger value, depending on how strict you want to be or how careful you want to be when you come to rejecting the null hypothesis. Now, Ronald Fisher, suggested 5%. Which is equal to p equals 0.05, or a 1 in 20 chance, if you think about it that way. To be fair, what he actually said was, some occasions it's going to be 1 in 20, other occasions might be 1 in 50, maybe 1 in 100, maybe 1 in 200. But everybody just heard 1 in 20, and for millions of students in the generations that followed, pretty much stuck to the magic number of 0.05, as if that had some sort of totemic value, that if the number fell beneath that, you didn't have enough evidence to support the null hypothesis, and the number was above that, you did have enough evidence to support the null hypothesis. And the problem about choosing a single number is it becomes like a fruit machine. It's either, the test becomes real. It's either up or down. It's either, yes, you've got COVID, or no, you haven't. Yes, it's significant, or no, it's not significant. In reality, it's just a number, and it's a pretty arbitrary number. So on this basis, if the probability is less than 0.05, we would therefore reject the null hypothesis on the basis that there is insufficient evidence to support it. And that's the context within within significance testing, that these p-values link up with null hypothesis. There is this kind of somewhat weak arbitrary point that connects the two, where you either accept or reject null hypothesis based upon a agreed upon threshold. In social sciences, it does tend to be 0.05. In things like clinical research, and particularly things like drug testing and stuff like that, they tend to be a bit more strict, tend to be 0.01 and sometimes 0.001. So the alternative hypothesis actually is there for reference only. We never accept or reject it based on our analysis. So if the p-value is greater than 0.05, we don't accept the null hypothesis, the alternative hypothesis. We don't say, all right, well, we can't reject the null, so therefore we must accept the alternative. It's only there for reference. We don't say anything about it. In fact, we never even accept the null hypothesis. The most we can do is find enough evidence to support it and therefore reject it. Some analysts argue this is a real limitation of classical frequentist statistics. Those analysts tend to be Bayesian analysts, and in Bayesian statistics, they have an alternative approach to hypothesis testing where they compare how much evidence there is for the null hypothesis versus the alternative hypothesis. They actually come up with a ratio value and tells you how much evidence there is for one group or the other. Whereas in classical frequentist statistics, you just either reject the null hypothesis or you don't. And you make it's truly one-dimensional. It only goes in one direction. It doesn't go in two directions at once. And we actually have some videos that you might want to look up on the alternative approach to this approach, which is the Bayesian approach as opposed to the frequentist approach. Okay, returning to our interpreting p-values, contrary to a lot of statistical teaching, the p-value does not indicate the probability that the null hypothesis is true. This is a misunderstanding. It also does not indicate the probability that the data were produced by random chance. What p-values can do is indicate how compatible or incompatible the data are with a null hypothesis. And that might sound like semantics, but it's not. For example, the probability of x given y, x in the universe given y is not the same as y in the universe given x. So what's the probability of somebody having a full driving license given they're age 17 or over? Might be about 0.75. I think it's about 75% of people age 17 or over in the UK have a driving license. Versus what's the probability of somebody being age 17 or over given the fact that they have a full driving license? Well, you have to be age 17 or over to get a full driving license. So if you've got a full driving license, then the probability is 1. You know, it's 100%. It should be theoretically. So it's 100%. So the two things aren't the same. And that's why the semantics are important. Therefore, the probability of a null hypothesis being true given the evidence is not the same as the probability of getting that evidence assuming the null hypothesis is true. And that's why the language is important when we're reporting a null hypothesis, of getting it right. So to reiterate that, the null hypothesis is pretty important. What are we saying here? We're saying how compatible and incompatible the data are of a null hypothesis. Let's look at all the different types of null hypotheses one can come up with in these tests of significance. There's lots of different types. And to correctly interpret any significance test, you must know the null hypothesis associated with it. So here's some examples. For a chi-square test, the null hypothesis is that the two variables are independent of one another in the population, i.e. they're not related. So there's no relationship between them. For a t-test, which we've just seen, or sometimes an f-test, which looks at more than two groups, f-test looks at 3 or 4 or 5 groups, is that the group means are the same in the population, the same value. That's the null hypothesis. And for Pearson's correlation, it is that the correlation value in reality is actually 0 in the population. There's no linear relationship at all there. For Levene's test of equality of variance, it is that the groups have the same standard deviation, the same spread in the population. And for something like a Kayes-Lilliefors test, it is that the variable is normally distributed in the population. This is really confusing for a lot of students, because when they do a Kayes-Lilliefors test and it comes up with a probability of less than 0.05, 0.04, let's say, what they're doing is they're rejecting the idea that the data is normally distributed in the population. If it's above 0.05, it's like 0.07 or something like that, then there isn't enough evidence to reject the idea that the data is normally distributed. And you say, my data is normally distributed. And because they tend to think of the hypothesis test as the probability of showing something interesting, and because they tend to think that your data being normally distributed is the interesting thing, they think that a value less than 0.05 should lead them to conclude that the data is normally distributed. But it's incorrect, because we have to understand what the null hypothesis is for each test. And the null hypothesis for a normality test, such as Kayes-Lilliefors, is that data is normally distributed. That is what we are accepting or rejecting. Sorry, that is what we are potentially rejecting. We never accept it. So let's look at crosstabs and chi-square. Let's look at a worked example here. So crosstabs are a powerful way to examine the relationship between categories. And the chi-square test is commonly used with crosstabs as an associated statistical test. You'll get these in in SPSS. So here I have a crosstab of what was that? That was gender against employment category. So I'll just go here to analyze, down to descriptive statistics, down to crosstabs. I'll put gender up here and put employment category in there. So that's exactly the same situation as you're seeing in the slides there. So, okay. If I run that, this is what I'll get at the back of it. It's just going to show me some frequencies and say there's 206 female clerical workers, there's 0 female custodial workers, there's 74 managerial workers, 157 clerical workers. So they normally display this frequency counts. But they're hard to interpret because, of course, the group sizes are different. We've got 216 females and 258 males. So what we do, we add percentages. We say, well, off the percentage within the gender, so off the percentage with who are female, 95% are clerical workers compared to males, where only 60% are clerical workers, 61%. 4.6% of females are managers compared to 28.7% of males. Okay. In this example, we have row percentages, so we can compare the genders in terms of employment category. Okay. But it turns out crosstabs can also display what are called expected counts, expected frequency counts. And these are worked out by taking the row total for a cell and the column total for a cell and dividing it by the grand total. And that will give you the expected count. In this case, is 165.54. So it's saying, I know you got 206 female clerical workers, but if gender didn't make a difference here, we'd actually expect a few less. So if we were adjusting for everything and distributing it evenly based on the group sizes, the different group sizes, you'd actually expect to get about 165 in there. So you're actually getting a few more. You're getting about 40 more women in that group than you would expect if they were kind of evenly distributed with respect to the different group sizes. So expected counts are really important because it turns out that the difference between observed and expected counts, in this case 40.6 here, are called residuals. And if you think about it, if you get a crosstab where you get a load of residual values, which are quite large residual values, then you're seeing a lot of examples where, where you're not seeing the same frequency counts as one would expect to see if things were evenly distributed. Now, if I added up all these residual values here, they'd come to 0 because, it's 40.6 minus 40.6. If I add those together, obviously come to 0. So what we do is we tend to square the values. And these are called squared residuals. And squared residuals, of course, a residual of minus 3 is therefore going to become 9 if it's squared. And that's where the chi-square bit comes from. So if we add up all the squared residuals, that's going to reach a value where the larger the number, the less likely it is that the variables are unrelated to each other in the population, because we're seeing bigger differences between the observed and expected. In the same sense, if we flip a coin 100 times and it comes up 75 times heads and 25 times tails, we know what the expected frequencies are. The expected frequencies are 50 and 50. So we can say there's a bias of 25 more heads than you expect to get, and you're actually seeing 25 fewer heads than you expect to get in the other group, or for fewer tails than you expect to get in the other group. So we can calculate that kind of fairly naturally. It's just that squared residuals here are a way to formalize that, to look at the difference between the observed and expected, and we can add them up and summarize them, and the result is a Pearson chi-square value. So that's this value down here. Now, it's a little bit more involved than that, but that's the principle behind it, is you can add them all up. So the bigger this number is, the bigger the difference between the observed and expected across the crosstab. And that allows us to then say, well, how often would you see a difference that big? In exactly the same way that if we were to flip a coin and have it come up 75 times heads and 25 times tails, we can say, how often would we expect to see a difference that big? So the null hypothesis, as we know, associated with chi-square test, is that the variables are unrelated. And a small probability value, therefore, of less than 0.05 indicates that differences as large as the ones observed will only occur quite rarely if we assume this null hypothesis is in fact true. And we would therefore reject the null hypothesis. So you can see here that the difference here is 0.000. If I just run back to SPSS here, I can go to sales and I can see I can ask for expected counts and I can ask for row percentages, and I can go to statistics here and ask for chi-square test and click continue and OK. And here's the results. There's my probability values, exactly the same as we see. Here's the expected count, here's the actual count, here's the percentage values, and here's my chi-square value here. Nowadays, it just labels it with less than, saying it's smaller than 0.001. That's the default labeling. And there's the chi-square value associated with that. So how do we interpret that? Well, what we're saying is that the chi-square test indicates that the probability of obtaining our value as extreme as the one observed, which is this value here, 79.277, with 2 degrees of freedom, is less than 0.01, assuming the variables gender and employment category are unrelated. Given this result, there appears to be insufficient evidence to support the null hypothesis, and it is therefore rejected that the two variables are in fact unrelated to each other. And that is kind of the formal way to interpret that result, crosstabs and chi-square. And that's our first test of significance. It doesn't mean it's interesting. You know, this could be like, you know, this could be quite mundane, you know, just who plays golf at the weekend or something like that. It doesn't mean it's particularly significant or anything like that. It doesn't mean it's significant in that sense. It doesn't mean that you could go and you know, get a different sample and get exactly the same results. They probably vary. But what we're saying is that as regards the notion that in the population that this sample is drawn from, that men and women are no way related to or affected by employment category, or vice versa, that employment category is no way related to gender. There's no direction assumed here. You know, it's just looking at two groups, two variables. The idea that they're no way related, there isn't a lot of evidence to associate that. And because the associated p-value is less than the arbitrary level of, let's say, 0.05 here, which is, let's say, the most common arbitrary cutoff point, the alpha level, we would say there's insufficient evidence to support the null hypothesis and is therefore rejected. Okay, so that's our first one. What about a different situation here where we're not looking at category fields, where we're looking at correlation coefficients and the dangers of talking about significance? Well, here's a scatter plot, and this scatter plot shows a strong linear relationship between salary and beginning salary. So this is people's current salary in the same data set, and this is their beginning salary, and you get the scatter plot, and it basically says, yeah, these two things tend to be related to each other because they're forming this line, and it's just basically saying that, you know, the larger your beginning salary is, the larger your current salary is, and vice versa. The larger your current salary is, the larger your beginning salary. Again, there's no direction. There's no implied direction here. So correlations are used to measure the strength of these scatter plots, the linear relationships in these scatter plots. In these scatter plots here, we're going to return to correlations in the next webinar, and we're going to look at it in much more detail, how it's calculated, etc., and what different types of correlations. But if you assume that this correlation here is looking at the relationship between cars of different types, so each of these dots represents an automobile, and we have recorded the horsepower and the vehicle weight. And the correlation value here is 0.859. That's quite a strong correlation. Whereas here, we're looking at the relationship between miles per gallon, the fuel efficiency, and the time to accelerate from 0 to 60. It's saying if it takes longer to accelerate to 0 to 60, the fuel efficiency tends to be higher. But you can see it doesn't form as tight a line as this scatter plot here, and therefore the correlation value is slightly weaker at 0.434. This is a negative relationship here, minus 0.701. This is the relationship time to accelerate from 0 to 60 against horsepower, saying that if you've got a lot of horsepower, you can accelerate from 0 to 60 a lot quicker. And that's a negative relationship. So here the relationship is actually has a it doesn't say that one causes the other, but there is a direction to it. It's a positive direction. As one goes up, the other goes down. It's not saying which one is dependent on the other. And these are Pearson, as again, Carl Pearson, same guy does Pearson chi-square. These are his correlation values. So you can generally glance at a scatter plot and make a guess as to what the correlation values are. The correlation values go from -1 to +1, so they can't go below -1, they can't go above +1. And the closer they are to 0, the more random the relationship is. So here we have a correlation value very close to 0, and it's the car's mileage against the miles per gallon. Well, the age of the car in no way is related to its fuel efficiency. So we just get this cloud of points, and that doesn't form a line at all. And the last thing here is that we have engine size against miles per gallon squared. I've done that on purpose to create this hooky symbol, this kind of hooky relationship here. It's kind of curved relationship. Correlations can't see curved relationship, they're blind to them. So it's assuming that it's just looking at the straight line. It is not looking at this curved line. So they're limited in that sense. They can only see straight line relationships, even though this is quite a strong correlation here, minus 0.671. So the closer they are to -1 or +1, the stronger the relationship, and the closer they are to 0, the weaker the relationship. Now, here are some correlation values for each pair of relationships between 4 variables. In the data set we just looked at, which had employees, we have their beginning salary, we have the months since hire, we have their previous experience in months, and education level in years. If we look at the stronger ones here, I've highlighted the stronger ones here. There is a strong relationship between people's beginning salary, 0.88, quite close to 1, and current salary. There is a weaker relationship between people's education level and their current salary, yeah? But it's just basically saying the more years of education you have, the higher current salary, and it's even slightly, it's also quite strong here, education level against beginning salary here, 0.633. The rest are quite weak. Look, they're all quite close to 0 relative to these numbers. So they're all quite weak here, so some of them are negative. It's basically saying there isn't a lot of relationship between how long you've been in the job and your current salary, and there isn't much relationship between your previous experience in months, which is going to be related to your age, I guess, and your beginning salary, or even how long you've been in the job. So the rest of these relationships are quite weak at this point. Okay. But which ones are statistically significant using that term? Well, that's a different question. That is a different question from saying how strong the relationship is. Because as we know, when we test for significance, we're testing in one direction. We're testing a very, very narrow thing, which is the null hypothesis. And you got to remember that the null hypothesis for Pearson's correlation is that the correlation value is actually 0 in the population, i.e. no linear relationship. So when we add in the significance values, which you get by default in a Pearson's correlation, you can see that some of these are very significant. It's saying the probability, effectively, the probability of getting a result as extreme as the one observed here, 0.88, in a universe where beginning salary in no way affects current salary, is very small. So we would reject the null hypothesis that what would we reject the null hypothesis? We're rejecting the null hypothesis that the correlation really is 0, in the population. In fact, it's 0.88 here. Whereas here, we have a really, really weak correlation here. It's quite close to 0, minus 0.097. But it's not so close to 0 that it becomes non-significant, what we call statistically insignificant, because that is that value there, that sig two-tailed value there, meaning that it doesn't care if it's a negative. Sig two-tailed means it doesn't care if it's a negative or if it's a positive relationship. It's still less than 0.05. So technically speaking, if we're saying our alpha level, our cutoff level, our arbitrary cutoff point is 0.05, and anything below 0.05 is, to use the dreadful term, statistically significant, then we're saying this is a statistically significant correlation, because we are rejecting the null hypothesis that the correlation between previous experience and current salary is 0 in the population. And we're saying instead, no, it's actually not 0. But it's not very strong, is it? I mean, it's 0.09. It's really, really weak correlation. It's not even 0.1. But it's large enough for it to be statistically significant. Why are we pointing this out? Pointing this out is that the ludicrousness of calling something significant doesn't mean that it's notable or interesting. You still get statistically significant relationships when the relationship is very, very weak. It just depends on the null hypothesis. The null hypothesis here is not testing whether or not there's a strong relationship between the two variables. It's saying whether or not there's 0 relationship between the two variables. So in this case, we're saying, is this statistically significant? Yes, because the probability of getting a result as extreme as minus 0.097, assuming there is no relationship between the two variables, is still only 3.4%. Does that mean it is notable or worth reporting? No, not particularly. But then that's not what the null hypothesis for Pearson's correlation value is directed at. It only states that there is no relationship there at all in the population. So that's why knowing what the null hypothesis is associated with a test is so important, because it's not saying this is a notable relationship. It's just saying that it's probably not zero. And that's not necessarily terribly interesting. Okay, let's come to our last example here. This is an example where we're comparing two averages. I didn't want to get into t-tests because t-tests are a bit too involved to shoehorn into this this particular webinar. But this is kind of like a sister procedure to compare two averages. We can use confidence intervals to compare averages. And I also pointed out, because it's one of the most commonly misinterpreted sort of loosely tests of significance or inferential statistics in statistics, to the extent whereby you can literally type in how to correctly interpret confidence intervals into Google, and the first hit you get is incorrect. That's how commonly misinterpreted it is that Google gets it wrong. So as you remember, different samples from the same population vary. You've seen this before. Okay, you can take different samples from the same population and get slightly different results. Repeat a survey or project and you won't get exactly the same results. Calculate a statistic, and the results vary from one sample to the next. No statistical calculation can tell you what the actual value of a population parameter is, and we don't normally have the luxury of repeating samples over and over again. But what we can do is we can often estimate a range of values that it is likely to lie within. So if you want to calculate an average and you say, well, I wonder what the average age is of people who, I don't know, who play board games is, or something like that, or the average age of people who, who like to go hiking at the weekend, you take a sample, you're going to calculate an average, and you know that average is probably not perfectly accurate. So what you can do is you calculate confidence intervals, which will give you a range of values indicating where the average is likely to lie within in a loose sense. So confidence intervals are often shown graphically as error bars. Look at these little TIE fighters here, where the circle in the center is the average, the mean, and then the upper confidence value, the range, the upper part of the range is shown at the top here, and the lower part is shown here. And sometimes they can be far apart, and sometimes they can be close together, depending on how confident the calculation is, obviously, and depending on a couple of other factors which affect the confidence, which we'll come to in a second. Now, it turns out that in SPSS, there's one procedure that will actually give you the confidence values directly for you. It's called the Explore procedure here. I'll just show it to you here. If I go to Analyze, down to Descriptive Statistics and Explore. Explore is really, I'll just pick age here, is really to really explore data. If I broke it down, if I put gender in there, it would give me 2 bits of output, one for males and females. It would separate them out for me, but I'll just pick age here. I don't like some of the plots, so I'll just switch them off. I'll switch on histogram, click OK here. When I run that, it just bombards that age variable and tells me lots of different statistics about it, the standard deviation, the minimum, maximum value. The minimum age was 21, the maximum was 63, the interquartile range is 17, the skewness and kurtosis values here. It actually gives you 95% confidence intervals for the mean age. Mean age is 35.58, and it's saying the 95% confidence intervals for this particular sample are 34.51. That's the lower part of the TIE fighter, if you like, and the upper part, the upper range, is 36.64. So it's saying that the mean age is likely to lie in the population somewhere between 2 points like that. Okay, I need to be really careful here with my language. Okay, so we'll come to that in a second. So 95% confidence intervals, what does that mean? This means that the mean age happens to be 34.74, but of course we don't know what the mean age for employees in the population of the sample really is. So the confidence intervals indicate it is likely to be contained in a range like 33.67 to 35.5 to 35.8. As we know, drawing another sample would probably result in a slightly different mean value. But it's not just the mean that would change. All the statistics would change. The standard deviation would change. The interquartile range would change. The skewness values would change. And the confidence intervals would also change. So if we drew another comparable sample, the confidence intervals would be probably different as well. In other words, we can't get too hung up on the values of the confidence intervals themselves any more than we can fixate on that value, 34.74. What we can say, however, is that even if the intervals vary from one sample to the next, they're likely to be broad enough that on 95% of occasions, they will contain the population mean, i.e. the parameter. And we have to be really careful here for our language. So that's why I've put that in red. They're likely to be broad enough, confidence intervals are likely to be broad enough that on 95% of occasions, they will contain the population mean, i.e. the parameter. What we can't say is that we are 95% confident that the population parameter is between X and Y. And that's because the intervals themselves will vary from sample to sample. And there's no scientific basis to the phrase we are 95% confident. And it is the procedure that on 95% of occasions will capture the population mean. Again, this is one of the reasons why people prefer Bayesian statistics, because in Bayesian statistics, ironically, you can actually say they have something called credible intervals, and you can actually say there's 95% probability that the mean is between these 2 points. But with confidence intervals, you can't. So I just need to be careful about that. It's something that statistics lecturers like to chastise students over. If I just go out into Google here, let me just go to Google and just type in, I don't know if it still does this. It used to a while back. How to correctly interpret confidence intervals. See that. Suggest you can be 95% confident that the population mean is between 9 and 11. That's incorrect. That's the first hit you're getting. That's absolutely incorrect. Okay. You can't do that. Instead, you got to say something like, I know it sounds like it's the same, sounds like it's semantics, but you got to say something like, they're broad enough that on 95% of occasions they will contain the population mean. So how do I prove that? Well, if we just jump out to SPSS for a second here, and just jump out, I'm gonna run a procedure here and just show you how confidence intervals change from one sample to the next. Let me just pull up a data set here. So I've got a data set here called I've got a data set here. It's got 3 million records in it. And what I'm going to do is I'm going to just hide my meeting controls. I'm just going to open up a syntax window and run some syntax here. Simulating confidence intervals. I'm going to run the syntax, and the overall average, I think, is 0.33 across this population here. The overall average. Okay, so that's kind of we're kind of pretending that it's a population. We've got 3 million records in here, and the mean value is 0.33, I think. And then we're going to calculate confidence intervals. But each time we calculate the confidence intervals, we're going to take a subset of 50 different cases each time. We're just going to sample the data 50 different cases each time. So here we have it. It says there's the population mean, 0.333, and the first confidence intervals we get are 0.251 to 401. And the second one we get, we're going to do this 20 times, remember? 0.224 to 3.52. Note that 0.333 is still within these confidence intervals. We would expect out of these 20 times, on average, that on one occasion it'll come up with confidence intervals. There you go, right? So right away, on one occasion there, it gets the confidence intervals wrong. So that was the 5th iteration, where the value is 0.333 and it's actually not captured by the intervals. And we can keep doing this, and we'll see if the remaining 19 times on average it gets right. Sometimes we do this example, and every single confidence interval captures the value of 3.33. And sometimes 2 of them miss it, but on average it's 19 times out of 20. So far, it looks like they're all capturing that value. They're all based on samples of 50 records from a population of 3 million records. We're up to the 11th one now. This one's got quite close to 3.33. Again, that's easily captured by this one. So we got up to number 13 here, 2.69, 4.27. Let's see this 14. Again, getting quite close to 3.33, but still capturing it. So the intervals themselves are shifting around from one to the next. We can't say that we're 95% confident that the interval is, that the true value is within these 2 points. We can say that 95% of the time this technique will produce intervals that capture the true population mean. So far, I don't think I've missed anything out. I think that all except the fifth iteration, the fifth sample we've taken so far, has captured the true population mean of 3.33. Here's the last one coming up. Let's see, 20th one. So it's got quite, so it's not finished. So 19 either 20 times or 95% of the times it captured the true population mean of 3.33. So as we're finishing up here, let's just figure out, let's have a look at how it does that. What information does it take into consideration to do that? Well, it uses something called a standard error. And a standard error, when we're calculating confidence intervals, we use something called the standard error of the mean. Now, there are other types of standard error statistics, such as the standard error of the median, the standard error of the difference, standard error of the correlation. These are useful for when we need to calculate confidence intervals for other statistics. A standard error is based on a standard deviation. Standard deviation, of course, measures the variation. It's the average variation within a sample. You've probably come across that before. But standard error attempts to measure the variation between samples. It tries to say, how much do you think that mean, that average here in this case, would vary from one sample to the next. And you can see it here. You sometimes see it very, very humble little statistic here, 0.542. And it's saying that on average, I'd expect this mean value here to vary from one sample to the next by a value of about half, 0.542. So that's what the standard error of the mean tells us. It's to calculate 95% confidence intervals, what you do is you take the standard error of the mean for that mean value, and you multiply it by roughly 2. 1.96 is the correct number because 1.96 is a special number that's associated with 95% in normal distributions. I'm not going to go into the deep math behind it, but it's roughly 2. In that case, it's going to give me a value of 1.062. If I take that away from 34.74, I get 33.678. And if I add it to 34.74, I get 35.802. So you basically take your standard error, you roughly double it, you take it away from your mean statistic, and you add it to mean statistic. That gives you 2 interval values. And that's how your 95% confidence intervals are calculated. So because the standard error is based on the standard deviation and the sample size, it actually takes into consideration the sample size. The width of the confidence intervals is therefore affected by 2 values: the size of the sample and the spread in the data, the standard deviation of the variable. That's because the standard error of the mean is the standard deviation divided by the square root of the number of cases, which is the size of the sample. So that means that confidence intervals get further apart. They get less confident, if you like, the smaller the sample or the bigger the standard deviation. And confidence intervals move closer together the larger the sample and/or, of course, the smaller the standard deviation. So that means that when I do a little chart like this and I look at men and women here, you can see that the female group here, the confidence interval is a little bit further apart. That can only be affected by 2 things. It might be both things at once, or it may be one of those 2 things. It could be that for age in the female sample, that the age standard deviation is larger, so there's more spread in it. Or it could be that it's a smaller sample, or both. So if you get a large sample with very little small standard deviations, the confidence intervals are much closer together. Now, why are they useful for comparing one group to the next? Well, they're really useful because it means that if I look at a group like this, here I've got 3. This is a bit like an F test. This is a bit like an ANOVA test. Notice the custodial group here. This is the smallest sample size, smallest group in the data set. So the confidence intervals move further apart because, of course, the standard error of the mean takes into consideration the sample size, and that means that the confidence intervals get further apart. And we can see here, very important, that the clerical workers and the custodial workers, the confidence intervals do not overlap. So note the custodial categories, And note that in the custodial categories, the composite intervals do not overlap with the other two groups. What does that indicate? It means that if you repeat the sample 100 times, generally speaking, the mean will always, for custodial workers, mean age will always be higher than for clerical workers and manager workers. And it means you can kind of reject the null hypothesis that the mean ages are the same for all of these groups in the population based upon the confidence intervals. So confidence intervals are a way to illustrate how means can be compared to one another and how a significance test like an F test or a T test works. Okay, just finishing up. There is some further reading around here that you might be interested in. We have a little blog series called Eat Your Greens, which looks at some of these concepts. You know, when something is statistically significant doesn't mean it's practically significant. The difference between testing and inferring. Why the standard deviation is so important. Finding normality. Why is the normal distribution so important? Why do statisticians always go on about? More information here about standard error and confidence intervals, understanding correlation, making sense of significance testing, and even an introduction to something called power analysis. So some further reading here. There's also a book called The Art of Statistics, which is a really good book. It starts from very, very basic statistical analysis, written by Professor David Spiegelhalter. It's really good. It's pretty accessible too. And you should just be aware that we provide a range of consulting services, which range from like 1 or 2 days of consulting time up to, more in-depth projects. And the best thing to do if you're interested in that is just to reach out to us, send us an email, and ask us if we can help, and we will try to do our best to come up with an estimate of the best way to approach any problems or to help you out. With regard to working with Smart Vision Europe in general, you can source your SPSS software and other software from us. We'll also assist with the pilot and implementation of any analytical tools. You can buy SPSS software directly from us online, and we provide a range of training, formal and informal training, classroom and virtual, and custom course development. And we also offer technical support and no strings attached technical and business advice relating to analytics, whether or not people are customers of ours or not. So again, the best thing to do is just reach out to us. In the next session, we're going to be looking at correlation, take a much deeper dive into these correlation values I mentioned earlier on, how to interpret them, how they're calculated, different types of correlations for different situations and different types of data. So if you're interested in that, then please register for it, and we look forward to seeing you again in the near future in one of our new sessions. Thanks very much.